Hello and good afternoon to everyone. I am Ravina Jain, Associate Software Maintenance Engineer from Red Hat, India.
I am Kiran Belle, Senior Software Maintenance Engineer from Red Hat India.
So we are here to discuss about how we are going to secure the system call by using the two Linux feature, that is the eBPF and Secomp. So let's start. So these are the points we are going to discuss today, that what the system call means, and why we need to secure the system call, and as I have already said, we need two features, that is a BPF and Secomp. So we will see what the BPF is, why it is so important, then what Secomp is, and which issue the Secomp get mitigates, and how actually it secures the system call with the demo. So let's begin. First of all, what the system call is. So it is basically the interface or the gateway by which we can enter into the kernel space to access the resources like the memory, input-output subsystem. So let's consider an example. The users or user application want to write a stream to the console, that is a standard output. Then what he or she will do, he will just call the printf function and give the name of the file to that. So it will call the system wrapper function, that is nothing but the write, which is inside the C library. Then it will go into the kernel space by actually calling the syswrite, which is the system call. It will get handled by the system call handler, and if it's successful, it will print the string onto the console. Otherwise, it will return an error to the user space application. Nearly 400 system calls are now available in the Linux kernel. I will show that in my demo. So why we need the system call security? So let's consider a normal application is running in the user space. It is calling the system call that is handled by the kernel, and the flow is getting normal. Okay. So if some malicious code enters and it will become a part of your code, then it can actually alters the behavior of the application by calling a system call function which is not intended by an application. So here comes into the picture, we need to secure the system call to improve the system stability. So as I discussed, it is by using the BPF and Secomp. So now we'll see what the BPF is. It is a Berkeley Packet Filter, and name itself suggests that it is used for the packet filtering, but now it is not limiting to that only. So it has been evolved, and now it is used in the many application, and one of that application is to securing the system call. Yes, to observe the system, we can use the BPF. Then for the security and for the networking, like it is controlling the traffic of the network at the kernel level, and that's why it reduces the overhead of copying the network packets from the kernel space to the user space. And it is getting evolved, and now it's called as a eBPF or the extended BPF, although the base is the BPF. So now it supports the 64-bit machine also, and we have the BPF system call wrapper function, which directly interacts with the BPF code. The eBPF verifier is also getting added. Because of that, it takes care of the other application and the flow of the code. eBPF should not crash your code. So, and it's getting still evolving. And eBPF is also used with the Secomp to secure the system call, and that is the topic we are going to discuss in the further slides. So now why eBPF is? One of the application or one of the use case is like, let's say you want to, application developer want to observe app, and it needs a feature in the Linux kernel itself. So what he will do, he will go to the kernel developer and say, I want this feature in the Linux kernel to observe my app, okay? So what the kernel developer will say, okay, let me think, is it good for everyone or not? So it will take a time. So once it is convinced like it is useful for the everyone, then it is getting added to the kernel feature, that kernel. And yes, almost after 1 year, the feature is getting supported by the kernel, but not by the Linux distribution. So as everybody is using a different distribution like Ubuntu, RHEL, Fedora, so like user wants to add it in the his distribution, Linux distribution. So it will again almost take a time, and at the end the requirement may get changed. So here the eBPF comes into the picture, where like again the application let's say need to observe his app, and he will go to the eBPF development. Okay, so the kernel can't do this in a short duration of a time, so it will get quickly solved by the eBPF developer. Why? Because we do not need to reboot the machine after getting added the feature by the eBPF. So this is the story, and now we'll move forward to how, like, as we are using the Secomp and eBPF to secure the system call. Now let's move forward to see what actually the Secomp is. So Kiran, over to you.
Okay. So what's Secomp? So Secomp is nothing but the secure computing. It's a fundamental security layer implemented in a Linux kernel. So what it does, it specifically allows the specific system calls from the user space and the user space to the kernel space. So suppose, as Ravina explained, the system call, suppose one application has specific load, the application makes the write system call that flows from the user space to the kernel space. So it tries to request to the kernel to access the resources like CPU, RAM, storage, and network. So there is the only way via system call. So Secomp implemented Linux kernel, it watch the system call. It's nothing but the gatekeeper, and it watch the system call which system call is coming. So if there are strict policies and rules that is written in the Secomp that is getting loaded in the Linux kernel, and Secomp decides according to that strict policies which system call needed to implement run in a Linux kernel or which not. And suppose user space, some application runs in a user space, and there are limited system calls are running. Application calls the limited system calls running, but suppose it don't call the required unintended system call. So Secomp sees that and it blocks that system call and return error to the user space. So Secomp is used for the sandboxing applications. So sandboxing is nothing but run your application in secured and isolated environment. So there are many applications uses sandboxing. So it's basically used for the limiting the system calls. So now I will take you through there are few vulnerabilities that is mitigated by the Secomp. So there are real-time use cases. So here one of the use cases is that CV found in WebKit rendering engine. That's the CV 2022-2620. This is nothing but arbitrary code execution. So what this vulnerability is? This vulnerability is nothing but the buffer overflow of a WebKit rendering engine. So once if attacker try to exploit this vulnerability, he put so much information to the web server. Like suppose you take an example that if you are browsing the internet, you open one website, and it has this flaw. Okay, so what will happen then? That if it has this flaw, when malicious code get entered, so it get access and he tries to execute the buffer overflow, and due to that it tried to execute. So there are few system call get called that nothing but the execv or mount. He tries to mount it. He tries to get access of using set GID, set identity. Those system calls will get called, and that is nothing but the malicious or compromised system. So how this mitigates by using Secomp? So here you can see attacker goal is to spawn a shell that will have a root access. So he will do anything what he wants to do. So what Secomp do is there are two modes basically, the strict mode and the filter mode. So nowadays there is filter mode is getting executed many times because the strict mode has only limited system calls, that is read, write, exit and sig return, but in filter mode any system call is allowed. So how it mitigates that, it restricts the only limited system calls, that is execv, set UID or get UID. That means that user will not get the, so when malicious code tries to access the execv, it will restrict that execv system call. So it will get mitigated because it will return error to the user space application. So this is another vulnerability found, and that is mitigated by Secomp. That vulnerability has that triggered the multiple infinite loop of process creation. So in process creation, fork system call will get called. So malicious attacker tries to exploit it by calling the multiple fork system call that gives the too many usage of the memory resources, and it will give the slow responses to the user. So that is mitigated by Secomp by restricting the fork system call to create and the clone to creating the and as well as the mmap. Mmap is a system call which called when you want to get the memory resources. So it is the normal flow here. So here what happened, so in user space, user application, so set component, that means use the filter or restrictions policies are getting attached to the user application, and it uses the C library wrapper function. So whenever application runs in a user space, it calls specific system call and it transits from the user space to kernel space via system call interface, and there is in kernel space Secomp data structure and BPF execution engine implemented and compiled. So whenever a write system call getting executed, it transfers to the kernel space. It sees that execution engine, all the information of system call given to the BPF execution engine, and this is nothing but the system call number, architecture, all this information put to the BPF execution engine, and system call handler will run and it will execute the syswrite. If that specific system call is not allowed, it will return error to the user application, that's write system call, and it will block the user process here. And if it is allowed, then it will display on the console. That's the normal flow it has. So we will see ahead that how it actually works by a short demo.
Okay, so let's start with the demo.
Okay. Sorry. तिकडे घ्या, move it to right. Alt tab.
ls command as normal, which displays list out the directories. Okay, so we'll see what system call the ls is doing. Okay, so these many are the system call which ls is doing. So we'll try to block one of this system call, and what eventually it will do, it will not means ls command will not get work if we block the system call using the eBPF and Secomp technology of the kernel. So let's consider we are trying to block the closed system call here. So the closed system call is having a specific system call number which depends upon the architecture and the operating system, and will throw the error number, and it is also we have the choice to throw the error number depend upon the situations or the application. So there are different files in the Linux system, that is a unistd.64.h, which is having the system call numbers, and the error base number.h, which is having the error number. So I will show you that. So is it audible? Okay. See, like here you have this many of the system call, and which is having the specific system call number. Let's say like hash define nr close having the 3 as a system call number. Okay, and the other file is list down the errors. Okay, so we'll try to throw the error as an operation not permitted, which is having the number 1. Okay, so let's move. So I'm again running the ls command. This is the C code which is trying to block the system call, the closed system call. So let me compile this code. So it gets compiled successfully. The executable get generated, that is the a.out. Let me run that. So it needs some system call arguments, like command line argument, which is a system call number, which we have seen, that is the 3 of the closed system call we're trying to block, then error number, and if the program and the name of the program, that is the ls command. Okay, so I will just try to block the closed system call, that is the number 3, and the error number I will show 3, and then the name of the program. So see, here we are getting the message as error while loading the shared library. The cannot close the file descriptor as operation not permitted. This is like how we are blocking the system call. Let's say we have a second example of this. So this is the system call is done by the ls command, right? So we'll take one system call which is not getting called by the ls command, and we'll try to block that, and eventually it will not block because it is not called by the ls command, right? So let's take the example of, I think, stat system call, which is listed here. So yes, a.out. The stat system call is, I think, having the number 4. I will try, and so see, the stat system call is having the 4 as a system call number, which is not called by the ls command, and I tried to block that, but it is not getting blocked because obviously it will not block as it is not called by the ls command. So it is listed as it is what the ls command is behaving in a normal situation. So yes, this is the demo of the filtering the system call. Yes, now we will move forward to the use cases scenario and the applications.
So quickly I will go through the program as well. I'll just brief it out, and then I will explain it very generically. So here, so first of all, it needs the prctl operation, and here is the install filter. Basically, whenever application runs, it needs the install filter. So every time the filter is getting installed here in the application, okay, and here is the BPF programs it uses.
So it will basically runs the BPF instruction to load the filters.
As well as here is the system call implemented in eBPF that loads the filter mode and calls the Secomp system call. So it's just the BPF programs that are loaded while running in a kernel. So I'll move to the So there are many real cases used where Secomp is used. There is OpenShift, Red Hat OpenShift platform, as well as the many it is used for the container security, Kubernetes, as well as the systemd uses the Secomp as a security feature.
These are some references we use, and you can go through that.
Any questions, and open for discussion and feedback as well. Yes. Right. So question is, what is experiences behind the system upgrades that uses Secomp or not, or it is implemented, how it is, right? Your question? So there are a lot of evolution or improvements going on. So many applications like Kubernetes or the containers, they are using even micro VMs, they are using as a security feature. And so there are a lot of things implemented via eBPF. This is not restricting to only a system called security. It's more than that debugging purposes, monitoring. There are a lot of things implemented by eBPF. So so that's the upgradation going on that part. Firefox, no. So Firefox. So the question is, is it the Secomp used in the Firefox? So Firefox has a different set of security implementation. This is a different, because the thing is, suppose take an example. The attacker wants to enter your application. Okay, so once he get entry, so there is second line of defense, that is nothing but Secomp. But Firefox, it's first line of entry. So in that situation, so Firefox has a different security aspect than the Secomp. It is not used in Firefox.
What are the logging facilities that allow you to understand that your program was terminated because Secomp because now you show the error code,
Right.
but if there is nothing in the system log, it's going to be quite hard to understand that
Right.
that the permission might came from a Secomp policy or some other Selenium feature or something.
So actually in the code, yes, so the question is like, what are the logging mechanism to understand if the Secomp is failing or the Secomp is used behind the security policy, right? So like we have shown that the system Secomp is the security or system call which we are going to use, and setting the mode of the Secomp filter. So it defined, and if it is not if it is giving the error, then it will show like the Secomp is not working or it is not there.
I want to add to this that suppose there are customized rules and policy we can decide, like that. Suppose whether this we can get the process ID, and according to that we can define the rules and policy, which system call intend to do restrict, or which system call is allow or disallow. In that case, we can define the rules, the customized rules that will load into the kernel.
And I will get information that it was the Secomp policy that blocked this and not some other security mechanism. Let's say, as an example, you had systemd could use Secomp to limit like a session or an instance.
Right.
So for that, we need to add some logging mechanism which will tell like it is by the Secom or by some other.
So there is, suppose you have one service, okay. So in that service, you can define I want to use the default Secom or I want to block the specific system call. So you can define in your service, and while that service is running, it will detect that if a system call is allowed or not. If it is not allowed, it will return error, and application may not executed in that case. Got it.
Any other questions? Can you repeat the question, please? I didn't understand. Can you repeat the question?
So I have a long-running process.
Okay.
I want to write a custom Secom profile for that
Okay.
application that I don't know the source for.
Okay.
And I know I can use Esprace like you did.
Yes.
So which system call?
Yes. Yes. Yes.
But Esprace is known to affect performance pretty badly.
Okay.
So is there some kind of approach I could take alternatively to using Esprace to get at the normal system call profile of some unknown application?
Okay.
So I will answer this. So there are different tools. Okay. So question is how can we implement the Secom profile if you want to customize for your application? That's the question, right? So answer to that is there are multiple tools available that BPF. There is BCC tools, the BPF trace, as well as that uses the Secom profiles. So you can monitor it, customize it according to that, and you can write your own customized code. No need to write the BPF instructions. There are multiple wrapper functions available that uses the BPF. So you can use directly those wrapper functions. So it will be easier to implement.
Any other questions?
Okay.
Thank you so much.
Thank you so much.